All right, here we go. 3.2, learning target. I can solve quadratics with complex solutions. And what this is going to start with is we need to be able to deal with negative square roots. And the way that we deal with negative square roots is something called imaginary numbers. Now, imaginary numbers, they're not real. So all I have to say is, welcome to
Wow! The land of make-believe!
These numbers aren't real. They are make-believe. They do have real applications, but again, they're not real. They're imaginary. Now, how this works, if I have the square root of some negative number, let's go with, they're using the variable r in the book. This is an imaginary number. And we need a way to represent this using some sort of variable. And the way we do that is with the letter I. That is our variable for an imaginary number. Now, if I have the square root of negative r, the way that this works is I'm going to take that negative, I'm going to clear it out of the square root, and it's going to go in front as an I. The r gets left behind. Another way to look at it is if I have the square root of negative 1, the square root of negative 1 is just I. That's what this is. So when we look at square roots, we can break them apart. For instance, if I have the square root of negative 25, I can break this negative 25 up into the square root of 25 times the square root of negative 1. Now, what this is, the square root of 25 is 5, and negative 1 square rooted is imaginary, it's I. So whenever I have a negative inside of the square root, I'm going to split that off as a negative 1 being square rooted. And this is for every single even root. We do this. And we really only see square roots that we're dealing with this. So the square root of negative 25 is 5i. We can have numbers that leave things behind in the square roots, so we need to be able to simplify radicals. So for instance, the square root of negative 72. I need to break this apart into something that's a perfect square, the negative, and whatever's left over. So when I look at 72, there is a perfect square in here. There's a couple ways of getting to it if we remember how. 72 splits apart into 2 times 36, which splits apart into, if we see a perfect square, we can usually just stop right there. That's a perfect square. So 2 times 36, 36 is a perfect square. So we're going to split this up. Square root of 2 times the square root of 36 times the square root of negative 1. Now, each of these things does its own thing. We have the square root of 2 doesn't simplify. The square root of 36, though, that's 6. The square root of negative 1 is I. Now, when we look at this, we don't want to leave it in this order. We want 6i times the square root of 2. We want it in this order here. So the coefficient is going to go real number, imaginary, square root. That's the order that we want it in. We could have things already multiplying in front. For instance, we could have negative 5 times the square root of negative 9. That's negative 5 times the square root of negative 1 times the square root of 9. Negative 5 times I times 3. Negative 5 times 3 is negative 15. Negative 15i. And that's what it simplifies to. So these are imaginary numbers. We can add imaginary numbers together. We can subtract imaginary numbers. But what we want to get into is complex numbers. So the next step in looking at these weird numbers are complex numbers. And complex numbers are of the form a plus bi. So a plus bi is a complex number. We have the real part. We have the imaginary part. And we can add and subtract complex numbers. We can multiply complex numbers. It mostly follows all our traditional rules of dealing with variables, though. We kind of treat I like a variable. So if we, for instance, look at the sum of complex numbers. The sum of complex numbers. If I have some complex number a plus bi, and I add it with some other complex number, we need new variables here, c plus di, what's going to happen is we only add like parts together. Reals go with reals, imaginaries go with imaginary. So those are the only ones that get to add or subtract together. So real with real, imaginary with imaginary. So if we have a plus bi plus c plus di, the a and the c get to add together. The bi and the di get to add together. So an example of that, if I have 6 plus 3i, that's a complex number. I'm going to add, let's go with negative 3 plus 5i. The reals go with the reals. The imaginaries go with the imaginaries. They don't get to intermingle here. 6 plus negative 3 plus 3i plus 5i. And you can, I'm sure you can do this portion in your head. 6 plus negative 3 is 3. 3i plus 5i is 8i. That is how they sum together. Subtraction, same thing. We're doing the same process. Let's go and write it out and do an example, though. Let's look at the difference of complex numbers. So here, same thing, a plus bi minus c plus di. And what's going to happen here is we're going to have a minus c plus bi minus di. Or in the book, they put b minus d, and then we just attach the I on the end. We're only subtracting or adding the coefficients together. We treat it just like a variable. So we treat the imaginary portion, the I, just like a variable. All right, here is the example. Let me find one from the book. 7 minus 6i minus 3 minus 6i. Now again, reals, go with reals. Imaginaries, go with imaginaries. We've got 7 minus 3, negative 6 minus negative 6. And we can have the i's inside, or we can attach it on the end on the outside. I'm going to go ahead and wrap those in parentheses. So 7 minus 3 is 4. And there should be a plus in between there. 7 minus 3 is 4, plus negative 6i minus negative 6i. Negative and a negative turns into a positive. Negative 6i plus 6i is going to give me 0 of those i's. That means it's gone. We have 4. So all we have to remember to do is treat I like a variable. I's go with i's. That's it. When we finish writing it and finish simplifying everything, it needs to go into that a plus bi form. So we can add or subtract complex numbers. We can also multiply complex numbers. So we can multiply complex numbers, but there's one thing we need to know here. If I multiply an I and an I together, that makes an I squared, but we can't deal with I squareds. We can't deal with I cubes. We can't deal with i's of any power greater than 1. We need to simplify them. So I'm going to give you what the rules are. We're not going to go through and derive them because it takes too much time, and I wouldn't want your notes to be super long. So here we go. If I have I to the first power, that's equal to the square root of negative 1. Take that back. I to the first power, we're just simplifying into i's. That's just I to the first power. So we just leave it as I. It is what it is. I squared. I squared is negative 1. I cubed is negative I. I to the fourth is 1. Now, after we go through this rotation, it just repeats. If we have I to the fifth, it's just I. I to the sixth, negative 1. I to the seventh, negative I. I to the eighth is 1. And it continues in this pattern of 4s indefinitely. So if we get I to some power, it follows a pattern of 4. First power is I, second power is negative 1, third power, negative I, fourth power, 1. So if we look, whenever we simplify, we're only dealing with an I to the first power, or a 1 or a negative 1. Now this is important when we multiply complex numbers, because we're going to end up with generally at least an I squared. I don't think there are any problems that we're going to run into that throw us into I cubes or I fourths. I don't see any in the book. So we'll stick to the I squareds at max. So examples. Let's start with something simple. 4i times negative 6 plus I. So what we have to do here is we have to distribute the 4i. 4i times negative 6. Well, negative 6 times 4 is negative 24, and we have an I. Plus 4i times I gives me 4i squared. We have an I times an I there. Now here I'm looking at an I squared. I need to replace this with negative 1. I squared, we're not dealing with it. That's a negative 1. So we've got negative 24i, and I've got plus 4 times negative 1. And again, this is something that you could be doing a lot of in less steps. Here, 4 times negative 1 is negative 4. I'm going to put that in front. That's my real portion. Negative 24i is my imaginary portion of this complex number. And we put them in order. Negative 4 minus 24i. Okay, let's do another example. 9 minus 2i times negative 4 plus 7i. Okay, this is a binomial times a binomial. 2 options here. Well, 3. We can just distribute. We can FOIL it, or we can throw it into a box. We can set it on the outside of a box and multiply into it. And again, I prefer using a box when I'm multiplying polynomials because it is a lot simpler. So I'm going to go ahead and multiply these into the box. 9 minus 2i, negative 4 plus 7i. Negative 4 times 9 is negative 36. Negative 4 times negative 2i is positive 8i. 7i times 9, that's 63i. 7i times negative 2i, negative 14i squared. And if we look right now, I squared, that's negative 1. We can deal with it before we even pull it out of the box. That's up to you how simply you want to go through this stuff, but let's just write everything out that we've got. This I squared, we have to replace it with a negative 1. Everything else we can start simplifying. We've got negative 36 plus 71i. This is negative 14 or minus 14 times negative 1. That's going to be a positive 14. Negative 36, positive 14. Negative 22 plus 71i. And that is our complex number. So this is an instance where we don't end up with a trinomial like we do with a quadratic. When we're multiplying factors of a quadratic, we end up with a trinomial in the end. We don't end up with that here because we can't have squared i's. It doesn't work. Okay, now the reason why we need to know this is because we can get complex solutions to quadratics. And the way we're going to see these is when we're dealing with a square root. That's the only time we see them as far as putting down I as a solution. So only when we're dealing with some way of square rooting it. Let's look at x squared plus 4 equals 0. So we want to solve this. We're going to use a square root. There's no bx term. We have an x squared. Let's solve it. We're going to subtract 4 from each side. We get x squared equals negative 4. We're ready to square root both sides. We're going to make a little space here. And we are going to square root both sides. Now on that number side, plus minus, because we have two solutions. The square root of x squared, that simplifies to x. This is plus or minus negative 4. Now, plus or minus negative 4, let's look at negative 4. We can split it now, or we can split it later. I like to split it now. X equals the positive square root of negative 4. X equals the negative square root of 4. Negative 4, sorry. Okay, the square root of negative 4 off to the side here. That's the square root of 4 times the square root of negative 1. If you are comfortable with it, just pull that one out as an I. The square root of 4 is 2. The square root of negative 1 is I. 2 times I is just 2I. So here what we've got, 2I, negative 2I. So those are the solutions. Let's do another one. Probably a couple examples of these. And this is the end of it. This is what we're here to do, is get the complex solutions to quadratics. If we want to, we can look at this graph on Desmos. X squared plus 4 equals 0. Let's go ahead and graph it up. And what you'll see is we do not cross the x-axis. So the reason why we have imaginary solutions is because our graph does not go through the x-axis. Normally our solutions are the x-intercepts, but we don't have any x-intercepts. That means that they're imaginary. They're not really there. They're in a completely different dimension than what we're seeing. They're imaginary. So whenever we have imaginary solutions, we should be able to graph it and see, hey, this is not going through the x-intercepts. If we graph it and we see it does go through the x-intercepts, we're doing something wrong. We're either graphing it wrong or we're solving it wrong. All right, let's do one last example and just call it good from there. 2x squared minus 11 equals negative 47. Now again, to solve this, I need to get the x squared by itself and then square root both sides. So I'm going to add 11 to each side. 2x squared equals negative 36. Divide both sides by 2. X squared equals negative 18. We're ready to square root both sides. Of course, if you want, you can leave space when you do that previous step and just throw your square roots in there. Okay, x equals plus or minus the square root of, I'm going to start splitting it apart now. Negative 1 times the square root of 2 times the square root of 9. 18 is going to break up into 2 times 9. 9 is a perfect square, so I want to use that. X is equal to plus or minus negative 1 is I. The square root of 2 is just the square root of 2. The square root of 9 is 3. And we just put these things in order as they come out of their square roots. So 2 solutions. 3i root 2. Negative 3i root 2. And we're going to need this for we can solve quadratics in this manner. We can also solve them using the quadratic formula, which comes up in a couple of sections. So we need to be able to do this and understand what I means. I think that's it. Let me just flip one more page of the book here. Yeah, I think we're good. Granted, there's going to be questions that are more complex, but the process is the same. You might have a fraction in there. You could have more steps to isolating x squared. You could have it in vertex form, but the process is still going to come out the same. We're still going to have the same process of solving for the squared. When we take the square root, if there's a negative in there, we're pulling i's out. That's it.